All right. I think I think we'll get started now. Feel free to leave any questions in the chat if you want me to go over something again, or if you need me to slow down, or if you need me to speed up. Um, all right. My name's Allan Pichardo. I'm one of the artists in residence at Babycastles. I'm also a computational artist and a software engineer. If you want to check out some of my work, you can go to my website. It's linked here on the notebook. Today we're going to talk about synthesizing audio with generative models. We're going to use a really basic generative model called the Variational autoencoder. The reason why we're doing this is because it's just easier to understand and it's easier to train this kind of model. I've provided some samples that we can use as the training data. However, if you have your own samples, that's cool. You can try that too. Um, like a lot of things in machine learning, there's a lot of trial and error, and it takes a long time to train this thing sometimes. So, just for simplicity, um, my samples are already sit in this notebook. Um, so we're gonna start off with some basics about the variational autoencoder, how to think of it in an intuitive way. We're not really gonna go into like the calculus or anything like that. Then we're gonna talk a little bit about the STFT, the short-term Fourier Transform, and what that does to our audio signals. And then we'll talk a bit about what's going to happen with our model, how it's going to work. It's all going to be very high level. And then we're going to build the model and train it here, and audition the sounds and see what comes out. All right. So first thing about the variational autoencoder, when for me it helps whenever I do anything with machine learning, it helps me to think of it as simply a function, right? Instead of it being a function that I write or a function that I derive, it's a function that the program derives on its own just by observing the examples, right? So just how you would have a function, y equals mx plus b for like a linear function, this would be just a function that has millions of variables. Now the real magic is that you can compose functions, right, to create more complex functions. And okay, let's just leave it at that, and let's go on to the next point, just so that we don't get too confused. The variational autoencoder, the reason why it works so well and why it's such a simple concept is because it consists of two parts: the encoder section and the decoder section, and they're basically mirror images of each other, right? So like you can give it an image, it turns it into a compressed representation, and then turns that compressed representation back into the original image. It's like saying you have a function where you plug in a variable, x, gives you an answer, and then you have a second function where you plug in that same y that you got from the last one, and it gives you back the x. So that's the overview of what's going to happen in the variational autoencoder. Why does that matter? Like, why is that relevant? Well, the reason why that's relevant is because when you have an image that goes in, you have all these pixels. There could be thousands of pixels. There could be millions of pixels. um, yeah, there could be millions of pixels there, right? But not all of the information is really relevant to that image. The autoencoder is able to compress it down into a small amount of information. So like if I had this input image here that's on my left, the number 1, and it turned into a vector of 5 values like this, then I could say, I could easily wrap my head around that and say, okay, cool. Like I can maybe, I can change this number, one of these little values, and maybe that'll have an effect on what the output is, right? And that's essentially what we're going to be doing. We're going to take the audio signal, the variational autoencoder is going to turn it into a small array of 8 parameters, 8 values, and those 8 values, we're going to manipulate them, and then on the other side, another wave is going to come out. That's going to be completely different than the wave that went in. And how it's different, it's not immediately obvious. As you can see from this graph, when there's inputs that have features that are similar, they get bunched up together in what's called the latent space, and that's just a projection of the distribution of those compressed representations. If they have features that are in common, they'll be close together. If they don't, they'll be far away. That's intuitively that's how it works. So how will this actually work for us? If we were to give an autoencoder just audio samples, it wouldn't work very well. I can tell you that it won't, because I've tried it. But you could probably make it work. It'll be complicated. But we need this to be a little bit simpler, because we don't have multiple days. So we need to pre-digest this information for the model first. We can turn the audio into an image by creating a spectrogram of the audio, right? And that'll make it very easy for the model to learn the features of the sound. And for that, we're going to use a function called short-term Fourier Transform. Without going into too many details, a Fourier Transform converts a signal that's a function of time into a signal that's a function of the frequency. So like, it takes a small buffer of the audio, maybe like 1024 samples or 2048 samples, and then it figures out the amplitude of the frequencies in that little buffer, and then it just concatenates with another buffer, and then another buffer, and another buffer, until you get the entire wave. When you do a Fourier transform, you get a complex number where like the real part is the frequency information, and then the imaginary part is the phase information. So as you can see from this image, one of the spectrograms, this is the second one here is the frequency, then the next one is the phase. We're going to put these together where one channel is 1, the other channel is 2, so it's like a 2-channel image. As for the purposes of the model, it's not really going to care, but it's just going to treat it as like one is one color and the other one is the other color. And then at the end, we're going to recreate the signal from that spectrogram. So essentially, our model is going to take this a spectrogram as if it was the input image. It's going to make some calculations. It's going to output a very small vector, and those are going to be our parameters for our synthesizer. and then it's going to try to recreate the original input as closely as it can, right, based on that latent vector. Do VAs understand time series, or are we just treating it as a bag of frames? Yes, the spectrogram does encode time. If and that's why we're using an STFT and not just an FFT, if that makes sense. If you use the STFT, is going to take a frame of like not a frame but a short buffer of audio, and it's going to concatenate them in order of time, right? On the x-axis. And on the y-axis is going to be the frequency. So it does encode the time. The VAE is not going to see it as a time series. It's just going to see it as an image where it's going to compare the information of the pixels in space. It's not going to compare values, simply across the x-axis. Though you can probably do that too. We won't do that in this workshop, but you can do a one-dimensional convolution that's time distributed. If you really wanted to look at it that way, you can. I hope that explains something. I know it's a very long-winded answer. All right, cool. So cool. All right, so this is our plan in a nutshell. We're gonna have a directory that has like a few thousand samples. These are all just like synth samples, pads, stabs, things like that I got from LegoWelt's website. If this guy's website is amazing. Like, he has a lot of really cool samples here. They're all free. If you want to, I'd recommend sending him a quick, maybe a donation or something like that. I donated a bit to him because his samples are just so good, and really this wouldn't have been possible without them. So we're just gonna have a directory of samples. It's gonna read all the samples, compute the STFT spectrogram of each one. It's gonna feed them into the network. It's gonna make the compressed representation of that, and then try to recreate the original spectrogram, compare the two, see how close they are to each other, and then convert the spectrogram back into audio. And at the end, when we do the training, we'll be able to listen to the input and the output and see how close they were. When the VAE is completely trained, we'll be able to cut this in half so that we only have the decoder part. That's really what we want. And we just, as input, we just give it the 8 values. And as output, it just gives us a sound. And you can imagine like what you could do with that. You can probably make a front end for that where you can have like knobs or sliders for the 8 parameters, and you can export your sounds and like use them in Ableton or MaximSP or wherever. Cool. So let's get started. Let's connect our runtime, and we should select. You can go to the go to the runtime menu here and select change runtime and select GPU. Otherwise, this will take very, very long. Cool. So first off, we just need to install like these libraries that we need for some of the audio processing. Then it's going to download the data set from my drive. if you want to, you can use this link and download it to your computer if you want. It's freely shared if you have the link. These are our libraries, and we're also going to clone the GitHub repo. Going to load TensorBoard and these variables, which I will explain to you in a few seconds. All right, this will probably take like a minute. If anyone has any other questions so far before we get into the coding part, just let me know and try to address that. So just to give a little bit more detail about how the autoencoder learns how to compress this information, there's this classic shape for the autoencoder. It's called the bottleneck. You know, you can think of the our spectrogram. It's going to be an image like that. It's going to go into the network. It's going to go through some computations, and then it's going to be cut in half, or it's going to be shrunk in half. Then there's going to be some more computations done, and then it's going to be cut in half again, or like shrunk in half. It's not going to be cut; it's going to be shrunk. And you can do this as many times as you can, right? Depending on like your specific purposes or like how robust you want this thing to be. And finally, when it gets really small, we're going to take all the pixels of this of the final image, and we're going to flatten them into a one-dimensional array, and those are going to be our parameters. And then on the other side, the decoder is basically an exact mirror image of the encoder. Just how like an image gets shrunk in half, shrunk in half. We'll just take the image, we'll expand it, we'll double the size, and then we'll double the size again until we get the original image out. All right, so just to go over quickly what this is. This network structured as a CNN? Yes, it is. It's going to be a CNN. Yeah, it is. Yeah, actually, there are cases where people use autoencoders to do translation, where you can like have like the input be like one language, the output be another language. And the cool thing about it is that the autoencoder is unsupervised. The latent representation that's here, whatever you can do to a vector in space, you can do with this, with the relationships between the latent vectors. And you can get really interesting things, like relationships between words. It gets really fun. It gets really interesting. All right, so before we start, I'm just going to go over like what these variables are. Just for reference, the sampling rate, 44K, that's the number of samples per second of the sound files that we're going to load. This could be different. You can change it to like 22, whatever, depending on like how much memory you have. However, I came up with these values when I was experimenting, and this turned out, worked out the best for me, so we're just going to go with this for now. The samples, we're only going to take 1 second samples. Again, you can take more. You can do like 2-3 seconds, but just keep in mind that that will increase the amount of memory necessary. And that will make it significantly harder to train. You'll have more parameters. You'll need more samples to train this correctly. So for now, let's just stick to 1 second. The batch size, this is just how many samples the network is going to see on every step that it does. This affects the memory, right? I can say like, I can make this 100 and it'll do like 100 at a time, but I know that Colab will probably crash because it'll run out of memory. Spectrogram shape, this is going to be the dimensions of the spectrogram. When we take the spectrogram, they're not going to be exactly this, but we're going to crop it so that everything is uniform. Latent dimension, this is going to be the length of the compressed representation, right? Essentially, we're saying we have 8 parameters, and those are the 8 parameters that we're going to tweak. You can make this bigger. The bigger this is, the more faithful the representation is going to be, the more accurate it's going to be. But the downside is that, you know, you can imagine if you want to make like a synthesizer out of this, you're going to end up with like 100 knobs. You know, it could be fun. I mean, I probably would like that, but to be realistic, you know, having like 8 parameters is a little bit more. Hamley's guy, when I play these steps, it's running on some kind of. It's running on their back end. Yes. Yeah. When it's running on their back end. When you click plus and you see like the thing spins, it's like executing it, and then there should be a result window that comes out here. If you are concerned about like privacy, etc., then you can always you can just clone the repository, and you can run this on Jupyter on your machine, or you can just run my code samples from the GitHub repo. All right, and finally, the number of epochs that we're going to train this for. The longer you train it for, the better it gets. But we don't have infinite time, and these steps are going to take like roughly 10 seconds per epoch. If we do like 100 epochs, it'll probably be like 15 minutes. So, okay. What we could do is while it's training, then I can address your questions. If we do 100 epochs, it'll be good enough, but it always can be better. All right, so here we go. Let's get started. So we have our input is a wave, right? So I like to do, when I do this, I like to do it in stages. So I'm going to break it down like this. I'm going to have one stage that converts the waveform into the spectrogram. Then I'm going to have one stage that does this part, which is the encoder. And then I'm going to have a third stage that is this part, the decoder. After we do the coding exercise and we get the sounds, I'll show you a short way to do this, because I made some handy little functions there. All you have to do is provide your samples, so you know, it'll get better. All right, so there we go. Here are our 3 stages, and I'll call this the STFT. So I'm going to start with the STFT stage. All right, cool. So every time you start, you can think of a neural network as just like a sequence, right? A sequence of operations. You do a calculation, spits an output. Then you take the output of that and you put it into something else, you get another output. You take the output of that, you put it into something else, you get another output, and so on and so on and so forth, right? So I'm sure everyone has seen the classic like image of this is called an MLP, a multi-layer perceptron, but everyone's seen images of these things. Think of it this way: you will start with like layer 1, then you do layer 2, and then layer 3, etc., etc. So at the beginning, where are we? Right here. So at the beginning, we take the input. It's going to be a waveform, right? And the size of that waveform, because it's at a sampling rate of 44.1 kilohertz and it's 1 second, it's going to be 44,100 samples, right? A one-dimensional array of those. So the shape is going to be, I'm just going to cast that, it's going to be the sampling rate times the duration, and the second dimension is going to be 1 because there's only one channel of audio, it's mono. All right, we have the wave. The next thing we're going to do is we're going to convert it into the spectrogram. And for that, I'm using a library called Kapre. Really great library that does all of these transformations on the GPU. It's super fast. Mag phase, great. Input shape is this thing needs to know the input shape, so it's basically this thing that I copied. I know it's a little sloppy, but that's what that is. And then the other parameters, we don't really need to change the other parameters. You could if you wanted to, but for this workshop, just to keep it simple, we're not. Just to explain quickly, you can change the number of FFTs, the number of Fourier transforms that are going to be done, and that's going to change the size of your spectrogram. The more you do, the higher resolution, the more information you capture, etc. I'm not going to change any of it. Just going to leave it as it is. All right. So that is done, and we're going to put our STFT input through that. It's going to go through that. It's going to come out. Oh, yeah, sure. Sorry. Okay. Here we go. I hope that's a little bit better. All right, so we're gonna put our STFT into this function, and it's gonna turn it into a two-dimensional image. The first dimension is going to be the magnitude being essentially the amplitude of the frequencies, just like spectrogram you might see in other places. And then the second one is going to be the phase of the frequencies. Then we are going to use a normalization layer just to normalize all the images. This helps your model converge faster. You can skip it. I wouldn't recommend skipping it though, because it'll just take forever. It won't be very rapid. So just regular Keras layers that can backprop and grow that. Kapre has really great. These are not actually trainable. The STFT, they're just wrappers for the TensorFlow TF.signal functions, but they work with Keras seamlessly, so I use them for that. All right. The next thing we're gonna do TF.layer, TF.Keras. Layers dot they have these experimental layers, pre-processing layers, which are kind of nice. This one, what it does, it just takes the values, it does standard normalization, right? Converts it basically to a z-score. It's the value minus the mean of all the values divided by the standard deviation. All right, just gonna give it a name. Normalizer. All right, and then I'm gonna put X back in there. So you can see the first layer is just our input. The second layer converts that input into the magnitude phase, stores it in X. Then we put X back into the normalization layer, and then X becomes the normalized STFTs. Now we're going to crop them to that shape 80 by 1025 so that everything is nice and uniform. For that, I'm going to use a lambda layer. What a lambda layer is when there isn't already one of these nice Keras layers, you can just write a function, like a lambda function, and just stick it in the lambda layer, and TensorFlow will compile it to their graph operations. So what I'm going to do is I'm just going to call tf.image.resize with cropper pad. And this is going to take the spectrogram and it's going to crop it to the height, which is going to be 80, 1025. So I'm hard coding these values, but normally I like to use variables, but I know that because we have limited time, things are always going to be these dimensions. But that may not be the case if you start to experiment with like changing the values for the FFT, or if you change the values of the sampling rate, things will vary a little bit. All right, cool. So now we have it cropped. That is the output. We're just going to call it STFT out. Now we can wrap that into a Keras model. So STFT model equals Keras dot model. The input STFT input, and then the output is going to be STFT out. And then give it a name. And let's print it out so we can see what's going on inside. For that, you can use this handy summary function. All right, so just to reiterate what we did here, we created an input which consists of a one-dimensional array that of the size, our sampling rate times the duration. In this case, 44,100 times 1. This is going to be 44,100 by 1. Okay. Then we take that input and we put it into our STFT function, and the output that comes out here in X is going to be a two-dimensional image, right? Next thing we do, the next layer, we pass that two-dimensional image into our normalization layer, and it's going to standard normalize the values there, and that will be the next values that are saved in X. Then we take those normalized values and we run them through our resize and crop function, and that's our final output, which are our cropped STFTs. Then we make it into a model, and if we run this, cool. So this is just a summary of what's happening. You can see now the shapes of the outputs of these. Our input layer has 44,100 by 1. Then it goes into the mag phase. Then it becomes 83 by 1025 by 2. 83 high, 1025 long, 2 channels. Then it gets normalized. Nothing happens to the size. Then it goes to our lambda layer, which is the one that's going to crop. and it gets cropped into 80 by 1025. Sweet. So that's one of the, so we're good with this. Now we're going to do the encoder. All right, so same pattern. tf.keras.layers.input. And the shape is going to be, the input is going to be this shape, right? So we can just write that directly in there, 80 by 1025 by 2. All right, great. Next thing, this is going to be a CNN, a convolutional neural network. This could have been another thing, right? You can basically do anything that you want, but convolutional layers are very convenient for image data because they're able to look at the pixels and the neighboring pixels and compare them and do a convolution operation to basically convert them into another image. That is essentially, it's called a feature map, but basically it does edge detection, and then it does more edge detection, and then more edge detection, and then edge detection on those edges, and then edge detection on those edges, and in this way, it creates many images that have details about the thing that you input into it. So, okay, x equals tf.keras.layers.conv2d. You can do convolution in many dimensions. You can even have video where the convolution is, distributed across the frames. So it's really cool stuff. The number of filters. This is going to affect the number of parameters in your network. The more parameters, the more difficult it is to train your network. So we're going to keep it low for now. But again, the trade-off is that the less you have, the less features, the less information that it captures. So, there's always a trade-off. We're going to go with just 16, though. And then the kernel size is going to be the size of the kernels that do the convolution. So basically, it's going to be a 3x3 filter that goes through the image, looking at 9 pixels at a time as it goes through the image. And then the rest, I'm not going to change this, but I'm going to change the padding and keep it the same. What padding is when this 3x3 filter, right? It might get to the edge of an image. Let's say it gets to it's going 3x3, 3x3, 3x3. It might get to the edge, right? And you might find that there isn't a lot of space for the other 2 pixels, When you change the padding, you change the way that it behaves when it gets to the edge. And in practice, what this does is that it changes the way that this thing gets divided by 2. Either it gets divided by 2 evenly because it puts some extra zeros in there, or it divides by 2 unevenly and then rounds to the next number. I prefer to use same so that the division by 2 is always nice and even. So that's what happens. So we change the padding, and I'm going to put an activation function on this. The activation function just adds some nonlinearity to the outputs, or it constrains the outputs to a certain range. This is really what makes machine learning useful. Without getting into too many details. Remember when I talked about composing functions? You can have f of x, and you have g of x, and you can f of g of x and f of g of whatever of x. When these things are nonlinear, that allows a neural network to create very like arbitrary size, lines. And, that's basically where the magic happens. All right, so rant over. Let's continue. Now that we've done the convolution on the image, we're going to do the next step, which is we're going to shrink it in half. All right? And for that, I like to do average pooling. Okay, put the X in it. The average pooling is going to shrink the image by taking the average of the neighboring pixels, right? And that'll become this pixel. You take the average of like these pixels, that'll become this pixel, et cetera, et cetera. There's other ways of doing pooling. There's one, there's a method called max pooling, where it'll just look at these pixels, take the max value, put it in there. But for audio, I've found that, oh yeah, right. For audio, I've found that average pooling works best. If we go back to, and this is a trial and error thing. If you look at the spectrogram and you look at the neighbors of these pixels, if you simply take the max, you might be missing out on some of this information, because again, we're dealing with sound, right? So to me, at least, it seems that if you are playing an instrument, you have these two frequencies. These two frequencies, maybe one is louder than the other by a little bit. If you take the max pooling, you're going to completely neglect this other frequency. But because we're dealing with music and harmonics, you want a mixture of these frequencies, That's why I use the average. I hope that made some sense. All right, so back into it. Cool. So we did the convolution, and now we did the average pooling, and we've got our image of half the size. And now we're gonna go at it again. We're gonna do the convolution on this little one, on this medium one, and we're gonna shrink it in half again. And we're gonna do this several times. We can do it as many times as we want. There's always trade-offs. You can, you'll be losing some information as you go along, but at the same time, you'll be reducing your parameters, which will make it easier to train. A lot of things in machine learning are just, weighing the trade-offs and seeing what is best given the resources that you have. Yes, so 4 pixels equals 1, it'll be, yes, that's right, 2 by 2 divided by 2, so it'll be 1 by 1. Yeah, so that's true, yes. This is like some weirdness could occur with the pooling since it's cyclical, like 2 pi closer. Yes. I don't, I even lost count, but I don't know. I just, I don't know. I just kind of got obsessed with it for a while, and I've been kind of into this, like, oh, how can I do music with machine learning? I recommend like getting something like PyCharm and doing it there, because PyCharm has really good code completion, and that'll help you learn what kind of functions you need. I call it shopping. Yeah. Anyway, I'll go back to this average pooling again. Great. So when this thing comes out, it's 80 by 1025, right? This convolution gets done, it's still 80 by 1025. When this global pooling gets done, it's going to be 40 by 512, because it's the floor, right? I know it's not 1024, it's 1025, but it's going to be 512. Then this thing gets done, it's still 40 by 512, and then when this average pooling gets done, it's going to be 20 by 120, by 256, right? We can continue shrinking this thing. So let's go for like another layer. I'm just gonna copy and paste it since it's the same thing. When it gets to this layer, it's going to be 10 by 128. All right. I haven't actually. What I do is that I like to go to archive.org and just read the research papers there. There's some actually linked in this notebook at the end, some really great papers on synthesizing audio. So I'll go into those later. All right, so let's go for one more. Let's take this 10 by 128 and turn it into 5 by 64. We'll do the same thing again, and this is going to be 5 by 64. At this point, I don't want to continue because, oh yeah, Papers of Coda on YouTube, right? Yeah, I love this thing, and 2-minute papers also. So at this point, I don't want to continue shrinking it because 5 is not going to divide evenly, and then when I do the decoder, then I have to like pad it, and like you can, but I'm just going to stop here. All right, cool. At this point, I got to the smallest image that I wanted, and I'm gonna flatten it, right? You're basically unraveling the pixels into a one-dimensional array. Keras, layers, that flatten, boom. So now it's a one-dimensional array of length 5 times 64, whatever that is. 320, right? So it's 320 one-dimensional. All right, cool. So here comes the weird part, and this is the secret sauce of the variational autoencoder. The variational autoencoder, the reason why it works so well is that it doesn't just say, hey, input A gives you compression A, right? And input B gives you compression B. It's not discrete that way. It's actually a distribution, It says the probability of input A being this vector is this. The reason why that's good for us is that we can sweep across the values, We don't have to like say exactly this value will give me this sound. We'll say like, if I have, a range of values that are kind of in this ballpark, it'll give me a sound like this. So in order for that to happen, we're going to make one of the outputs be the mean. It's going to basically try to learn this. Using ReLU, is ReLU better for only certain use cases? I don't actually know. Okay, I haven't heard of ReLU. I'm familiar with like leaky ReLU and ReLU. In this particular case, it doesn't really matter much because you're not necessarily trying to constrain the values. You're just trying to add some like non-linearity, and it's up to how you want these values to behave in the latent representation. We could change these, you can change these right now if you want. Change them to like hyperbolic tangent or something like that if you want them to be between -1 and +1. I don't think it will make much of a difference in the convergence. All right, so see the Keras, layers, dense. And this one's gonna be, I'm just gonna type it explicitly. It's gonna be 8. And for activation, I'm just gonna keep it as none. All right. So what's happening here? The dense layer. Sure, we've all seen a picture of a neural network like this with these little neurons, right? These are called perceptrons. And when you put a lot of these together, it's called the multi-layer perceptron. Tito, sit. Dog is whining. The cool thing about these is that these work well with one-dimensional data. And the number of units that you use in that layer is going to be the dimension of the output. So we want this to be 8 values, right? We want to turn these 320 values into 8. So we use a dense layer for that. 320 is going to go, these 320 values are going to go into these 8 perceptrons, and it's going to be turned into an array of dimension 8. What do you mean by latent? I just learned what a latent space is, but I'm fully wrapped my head around. Sure, yeah. Let me go back up here for a second. So here's one example. The latent space is a projection of the vector that this hidden layer is going to make. Now remember, like we talked about the bottleneck, basically taking the image, shrinking it in half, shrinking it in half, shrinking it in half, shrinking it in half, shrinking it in half until it gets smaller, 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 end up with a nice little vector. Let's think of an ideal scenario where this vector is of size 2, right? If it's of size 2, we can think of it as x and y and just plot it on a graph. And if we plot it on a graph, we would see something like this, where the number 1, okay, the number 1 is blue, it's up here, and the number 0 is purple, and it's down here. They're in opposite sides of the graph because they don't have a lot in common. The 1 is like a stick, and the 0 is a circle, so clearly they don't have anything in common, but the 7, which is orange, is right here, right next to the 1, because the 7 and the 1 have things in common. They have this little stick part. You know, same thing with the 9. The 9 has a lot in common with the 7, you know, the top and the stick. This is what we mean by latent space. It's a projection of these vectors in low dimensional space, right? And by the vector, I mean that layer, that dense layer that we're writing now, that is going to be significantly smaller than whatever the input was. You know, this is 1, 2, 3, 4, 5 values representing an image that has probably, you know, 1, 2, 3, tons and tons and tons of pixels. I hope that helps. All right, cool. So one of the outputs is going to be the mean. It's going to try to learn the mean. We're also going to have it learn the variance. The variance is also 8 values. Activation none. You might be noticing that I'm doing activation. I'm doing none for my activation function in these. The reason for that is because I don't want the activation function is gonna clip your values, you know, and I don't want that, you know. For the mean, the variance, and the actual final embedding, I don't really want to constrain them. I want this to be any value, and then later we'll see the plot and see what it looks like. Kind of like CNN, the output of the convolution is called the convolution, and Encoder, the output is called the latent space. The output of the decoder is called the latent vector, yes, and yeah, the output of the decoder is that. All right, and then the final is going to be our Z. And I'm going to use the sampling layer. The sampling layer is a part of the repo that I linked here. It's a custom layer, so I recommend using the repo. Otherwise, you would have to code this yourself. And to be honest, it's like a little bit beyond me. But basically, what it's trying to do is trying to take the mean and the variance in this normally distributed, Gaussian curve. It's trying to sample a value, a normally distributed z value there. All right, cool. So z, it's going to output the mean. The mean is going to output the variance, and it's going to output z itself. Well, these are the inputs. I'm sorry. Sorry. And oh, go for it. Ask me as many questions as you all want. Yes. I don't think it would apply here. Yes, I don't think it would apply here. But I'm not really the person to ask about that because I'm not really an expert. I wish I had more information about that. But you can basically use any sort of network. You can arrange it into an autoencoder fashion. The autoencoder is just the architecture of the network, but the actual layers and the actual, the actual parts that learn things they could be anything, All right, so the encoder output is going to be, it's already out anyway. Let's make our model. What I mean by that is that what they call the autoencoder is just this shape. Exactly. It could be used with any network. It's just, it's just this bottle shape, this hourglass shape. If you can manage to do this with anything, like we could make it a multi-layer perceptron and just have dense layers all over. Boom, 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 boom. In this one we might have 100 layers. This one will have 50 layers. This one will have 25. You could do it like that too. You could do it with LSTM. You can have it. You can do it with basically anything. Bow tie shape, yeah, basically. The reason why we're using a CNN specifically is because we're dealing with pixels, and to get rid of those too. Yeah, you can you can feed it an image that's noisy, and then the output is like a denoised image. You can do the super sampling. This is how super sampling works, basically. Like NVIDIA's DLSS or whatever. It's basically this. You have like a low res image, put it into the encoder part, and then the decoder turns it into an up res high resolution image. Thanks, Simon. All right, so we're going to make the model. And the input, we're going to take the encoder input, which is the 80 by 1025, and we're going to output a list, which is mean. All right, cool, and let's print this. All right, so just to reiterate what has happened, we are taking the input of our previous stage, which is this 80 by 1025 image with 2 channels. That's what we have here. We're doing some convolution on that. We're taking average pooling to shrink it in half to 40 by 512, doing convolution on that, shrinking it again to 20 by 256, doing convolution on that, shrinking it again to 10 by 128, doing convolution on that, And now our final image of 5 by 64, we flattened it from a two-dimensional array to a one-dimensional. And we are outputting 8 values for that. 8 values for the mean, 8 values for the variance, and 8 values for a sample in that distribution. All right, cool. So let's print this. Oops, Z is not defined. Oh, oops, that doesn't go there. Fun 2. Oh, oops. Sorry, guys. This first layer is not X, it's supposed to be input because X hasn't been defined yet. Sampling. Sorry about that. All right. So, okay, so here we are. We can see that in this output, it's 80 by 1025, 80 by 1025. The reason why this is 16 channels here is because the convolution has 16 filters. Whatever amount you put in here, that's going to be the number of channels that that convolution outputs. So just keep that in mind because that affects the number of parameters, trainable parameters that you end up with. Okay, cool. So then it turns to 40 by 512, then 20 by 6, and 10 to 128, 5 by 64 by 16. Right. This isn't simply 320 because it's 320 times 16. It's 16 channels of that, which is 5,120. That goes into the dense layers and becomes 8. That's our encoder, all the way up to here, our 8 value array. So cool, that's done. Now we're going to do the decoder. The decoder is going to be a mirror image of our encoder. It's going to start with that 8, with that length 8 array, and it's going to reshape it into a two-dimensional array. Then it's going to, upscale it, and it's going to upscale it, and then upscale it, and then upscale it until we get the final size. Like RGB, correct? Yes. Yeah. The channels are RGB when you're dealing with images. They could be anything though. In our case, one is the frequency and the other one is the phase, and the thing thinks that it's colors, but it doesn't. All right, so let's go with the decoder. Okay, input shape. So what's going to be the input shape? It's going to be whatever our previous one outputted, right? It's going to be 8. Next, we are going to, we need to turn these 8 values into 5120 values. And the way that we can do that is with a dense layer, right? Because the number of units in that dense layer will determine the size of that output. So and this is going to be 5120. Put an activation on there. Cool. Now we have we're here. We have our 5120. We need to reshape these values into, a 16 channel image of 5 by 64. So we can use the reshape layer. Keras. All right, and the shape that we want to make is 5 by 64 by 16. And by the way, this is the clear input. All right. Now we're basically at this step here. We have a reshaped vector, and we're going to, I know that this is the pooling and this is the convolution. I like to do the convolution before the pooling just so that the network, it just seems to work for me better. You could probably do it both ways. It'll still work. I think this way works faster. So Keras has a layer called Convolution Transpose. We're going to do Convolution Transpose, which basically takes the output of a convolution, right? A convolution takes two functions and it creates a third one. And so we're taking this third one and converting it back to the originals. So we're going to use 16 filters just like before, kernel size of 3 like before, padding. All right, cool. We did the convolution. Now we're going to blow it up by 2. We're going to increase the size by 2 on both dimensions. This is supposed to be, yeah, upsampling. That's what it is. Cool. So when this goes in, this is a one-dimensional, like one-dimensional array of 8. The output of this is going to be 5120. The output of this is going to be 5 by 64. This is going to be still 5 by 64, but when it comes up here, it's going to be 10 by 128. And we can continue. Let's just copy this and do it one more time. And this one is going to be 20 by 256. So let's do it again. And this one's going to be 40. Whoops, that's not cool. What did I do? All right, this is going to be 40 by 512. We need to do one more time. And this is going to be 80 by 1024. We actually need this to be 80 by 1025, right? Because that's how we started. The STFT is 1025. So we need to pad this with one extra value. So there's a layer called 0 padding. And padding. So on the y-axis, we don't need to do anything. So it's 0, 0. On the x-axis, I'm going to just add one value to the right, 0, 1. So now this becomes 80 by 1025. We could end there. When I do the padding, I like to add one extra layer of like the convolutional transpose to like glue it all together, right? Because otherwise, just the 0 value. I don't know if that actually helps or if it's all in my head, but it's what I do. Tito, stop. All right. Okay. We're going to use 16. And finally, what comes out of this convolutional layer here is 16 channels. But our original input was 2 channels. So we need to do one more convolution here, which is going to be the final output that constrains it to 2 channels. Cool. So then the final output is 80 by 1025 by 2. I'm going to call this call it decoder output. So let's just make it a model. Decoder output. Okay, here we go. The input is 8, then 5120, then 564, 10128. Okay, just as we thought. Final output is 80 by 1025 by 2. So that works. Cool. So now we have our 3 stages. The one that converts our raw audio samples into the spectrogram image. We have the encoder network that takes the spectrogram image and converts it into a vector of 8 values, of 8 dimensions. And we have the decoder network that takes our vector of 8 dimensions. Where did the 16? And turns it back into a spectrum of 1025. Sorry, I'm reading a question. Where did 16 come from? 16 is the number of filters in these convolutional layers, right? Here. When the convolution occurs, right? This can do it multiple times. This layer can do it multiple times. It's basically running through the image as many times as you want it to go. Each time, yeah, 1 channel per filter, exactly. All right, great, you know. That's, yeah, so that's why it's 16. Okay. All right, cool. So now we have the 3 stages of our network. What we're going to do is just put it together into another model that's a composite of these 3 stages. It's going to do FTFT. The output of that is going to go into the encoder. The output of that is going to go into the decoder. And then we're good. Then we're ready to train it. All right, so I'm using this this VAE class. That this is also in the GitHub repo. It's a modified version of the model that is in the Keras variational autoencoder examples, but I modified it to work with these spectrograms, and I modified the loss function to compute the loss function based on the spectrograms and not on the audio samples. So I recommend using this. Yeah. Encoder, decoder. Sweet. All's good there. Run that. All right. So that's all we had to do to create the model. Now we have all of our models made. Now we can start to train it. The sound sequence class is another custom class that I made for this workshop. All it does is it looks at whatever directory you give it that has the samples in it. All this is just a directory that has other directories in it, and they all have tons and tons of WAV files. It's gonna recursively go through the directories, load up the WAV files, and just randomly feed them into the network. You also might notice that I didn't do a training and validation set. You should have a training validation set in real life when you're gonna do something that you actually want to be general and everything. We're not doing that for this case, just as an example, but all you would need to do is just like basically copy this thing and then just put the path to like some other place, you know. Right, and that would be your test data. All right, sampling rate, it's 44K, the duration is 1 second, the batch size is 4. Great, so let's load this. And now we are ready to compile and fit this. We're gonna go for 100 epochs. And this Spectrogram Callback, that's yet another class that I made for this workshop. Basically, this Keras lets you have callbacks that give you information updates while the thing is training. You can do anything you want in between the epochs. This is like more advanced stuff. It comes with a set of callbacks already for you, but the Spectrogram Callback, I wrote this so that we can see the spectrograms and we can hear, it converts the spectrograms back into audio so that we can hear what's going on. If you were to run this on your local machine, you could see these in real time, but since we're doing this in Colab, we're not going to be able to see the callback, see the tensor board until after the training is done, when training is going to take like 15 minutes. So while this happens, then I'll be taking questions. All right, so at first it's going to initialize a normalized layer with the mean and the variance of the test data. This particular one has like 4,000 samples. You probably want as many as you can get. You want millions if you could, you know. Once this once this calculates the mean and variance, I'll start the training. So here we go. The first epoch has this ridiculous KL divergence here that usually goes away by like the second or third epoch. If it doesn't, then something went wrong. All right, let's see what happens. It's not looking good, I can tell you that, because the loss isn't really changing much. That means that the network isn't really learning anything. So we need to go in and see why that is. Okay, let's just go through our stages just to make sure, like, you know, everything is supposed to be the way it is, and I'll look at my notes just to make sure I didn't miss anything. Yes, I see where it went wrong. All right, I know what I did wrong. So the final output of my decoder, we're looking at the decoder section here. Notice that this final layer has a ReLU activation on it, it actually should have no activation. Because the ReLU function, right? Can I do a new one here? Because the ReLU function, right, is 0 when x is less than 0, and then it's linear afterwards, right? So you can imagine that all these images, all these spectrograms, they probably have, they likely have negative values and positive values. Every single negative value has been cut off by that ReLU there. So what you want is none on the final one, so that it tries to, it has no restriction on what it tries to recreate. All right, so let's rerun this cell here. All right, and redo this. And we don't need to do that again. And now we can start the training again. It's going to do the same thing. It's going to recompute the mean and the variance. And it's handy to know the mean and the variance once we want to denormalize these values and turn them back into real samples. Let's see what we got. Great. So it's actually working, I can tell. All right. So just a quick explainer of what's happening here. The loss function for a VAE is not exactly the same as the loss function for, just any regular autoencoder or some other kind of network. The loss function here is a combination of the mean absolute error, which is just a regular loss function that's looking at the mean absolute error of the pixels, trying to get them as close as possible. Assignment, the last line of callback is operator not allowed. That is weird. I'm not sure. Operator not allowed in graph. I'm not sure why I didn't get that. You know what you could do? Try restarting your runtime, factory reset your runtime, and then try to rerun the code. But you might lose. You should copy these sections before you do that, and then rerun it and see if it makes a difference, Simon. But like I was saying, you have the reconstruction loss, which is basically you're looking at the pixels of the input and the pixels of the output and comparing them, see how far away they are from each other. That's what this reconstruction loss is. And then the KL loss is basically how these values deviate, how much these values deviate from the mean and variance. All right, so this is going to go for a little while, so I'm going to go here in the chat and see what we got. In terms of questions, if you have a bunch of questions, this is the time to ask them. We'll have to go back and learn calculus and linear algebra. If to be a practitioner, you don't really have to, but it does help to have a little bit of a understanding, especially of the statistical things that are happening. But you're not going to be like manually, doing these operations, so you don't really need to. It just helps to when you read a research paper and they have like all this math on it, it helps you to digest the research paper. But just full disclosure, like I'm not really that great at it. I did study computer science, but like I'm not I'm not at this level. How much data do you need? Say as much as you can possibly get. You always need more than you actually think. I read in a book that as a rule of thumb, it's recommended to have twice as many data points as you have parameters, because you can imagine that if you're like, manually, trying to, somebody gives you a table with x, y, and it's like 2, 4, 4, 8, and you need to, figure out the line of regression there. That's essentially what this model is trying to do, but with like millions of parameters. So like sometimes if you have more parameters than you have training samples, some of these are going to have like garbage information on them, and there's just not enough variation in the data to set those to real values. They're just there for no reason. You don't need them actually. So the more training data, the better. Speech recognition and vice versa. I recommend that you go to archive.org. Yeah. And you can, and just read like some of the stuff they have here for like music information retrieval. It's just super interesting. And look at ISMER. Let's see if, ISMER conference. Check out their resources because they have good information about stuff like this. Speech recognition, audio synthesis, etc. Okay. So, what's a good starter tutorial class for machine learning? I'm following along, but there's a lot that's going over my head. I recommend Keras is really good. TensorFlow has some really good tutorials, so I do recommend that you go to the Google Developers YouTube channel, and they have some intro videos for machine learning. Maybe later I can post to the chat some tutorials, or I can tweet them out. Why VAEs for these? Are they state of the art? What do I have to use for ML generated music? The reason I chose a VAE is because it's easier. It's not state of the art. So it's just simply easier to visualize, and it's easier to write the code for it than like something like a generative adversarial network. If you want something a lot more robust, a lot better, you want a GAN. A GAN will give you a lot better results, and that's like what most of the stuff that's on Google's Magenta website is built on. But yeah, that would have taken multiple workshops to get through that. Could you explain what the sampling rate is again? Okay, the sampling rate of 44,000. That's just the. That just means that for every second of audio, there are 44,100 samples for it, like 44,100. It's like the equivalent of pixels to sound, right? That's the resolution of your sound. So if we only have 1 second, we have 44,100. If you had your 15 seconds, it'll be 44,100 times 15. Quantizing the wave, that's exactly right. I haven't built my own GAN for making music, but I've played with the ones on Magenta, which are super fun. They have like one cool synth where you like sweep between different sounds, get these like really interesting sounds. Recommend checking this out. Looks like they made a hardware version out of it. That's cool. There's also more advanced architectures that do time-based, um, that do time-based inference, where like they predict frames of sound or frames of notes based on the previous frames of notes, and that's how you get like these meaty things like this one. I've never made one myself, so I don't know. All right, cool. So it did, okay, so we did 50 epochs. We can run the TensorBoard, and TensorBoard is going to read this log directory, and it's just going to show us like the progression of the training. Again, like if you were running this on your local computer, you would be able to run the TensorBoard and see this in real time, but because we're using the Colab, we can only do one at a time. Okay, so it's starting to converge somewhere around here. If we go into the image tab, we can see these are the STFT inputs that have been going into the network. And let's look at the outputs. They're not going to be great. I guess they're not terrible either. They could be better. You can definitely rerun this training cell and train it for 50 more. Train it for as long as you can. These are going to be better if you have more varied data, if you have like more sounds that are completely different, etc. I see, Simon. I'm glad you found it, man. So one notorious thing about VAEs is that they're super blurry, and that's like not great. The reason why they're blurry is because they're giving you this distribution of the data, right? Like it's not like an exact like this crisp line is going to be this value. It's like smoothed out. Because we're doing sound, it could be better, I will admit, but smoothed out sound isn't always a terrible thing. You can think of like reverb and things like that. It's like nice and smoothed out. Anyway. And the audio tab. Ooh, get ready for these things. They're not going to be super great. Let me see if I have my audio on. Cool. All right. So it's definitely learning how to create the sounds. They're not super varied here, but if we give it just random values, it'll be a little bit more varied. And also, if we train this for a lot longer, it should get a little bit better. I think let's go ahead and let me show you one more thing before I go, if I can. Oh, it's not there. Okay. Make sure that when is it in this line sampling? Make sure it looks like this. Just look at my line and compare it to yours. Right? We're calling these, they're in functions, so there's like one set of parentheses. And then there's a second set of parentheses where we have the arguments to that. Make sure that it's that pattern, that you don't have an extra set somewhere. All right. So we saw what happened during the training. We saw the graph of the loss, and now we can make. Now we can get into the meaty part and actually like make unique sounds from what we have. All right. Just keep in mind that this isn't the best model that you can probably make. You know, you should train it longer. It will get better if you train it longer. You should add more samples. It will get better if you add more samples, okay? All right, cool. So I'm gonna comment this line out here, and I'm going to write what this function is, but I wrote this function previously just to make things a little bit easier. We're going to write it from scratch just so you can see what's under the hood, per se. All right. So our autoencoder, remember, works with spectrograms and outputs spectrograms, right? But we need sounds. So now we're getting to the point where we need to convert the STFT spectrograms back into audio samples. So how do we do that? If you recall from this image up here, the STFT consists of these two parts, right? The frequency information and the phase information, and one is in one channel, and then the other one is in the second channel. You know, we need to convert these back into complex numbers, where like the real component is the frequency information, and the imaginary component is the phase information, and then we will use an inverse STFT on that to turn it back into sound. So let's do that. Okay, so let's just do layers.input. And this is going to be our STFT, our spectrogram shape, which is 80 by 1025 by 2. Then we're going to take the decoder part of our autoencoder because we already trained it. We don't want to make a new one. We want to take the exact same one. So a decoder, and into there we put I totally screwed up. Forget everything I said. This is going to be this. Why is that? Because we actually cut it in half, right? We cut this in half, and we're getting rid of the encoder part. So we don't care about that anymore. You know, the input of the decoder is just our 8-dimensional vector. So we're only taking the decoder. So the input is 8. All right, cool. So the decoder takes the synth input. All right. Now, the output of the decoder, that is the spectrogram, right? So we got to turn that into a complex number. For that, I made a function, and it's part of the repo. Basically splits the two channels and then converts it back into complex. I don't think it's a good use of time to get into the math of that. I think it's better just to use the function that I made for this. So I'm going to use a Lambda layer. And I'm going to invoke my function, magface to complex, and that's going to take the spectrogram. Cool. All right, next. Now that we have this turned back into complex numbers, we will run the inverse STFT on it. There it is. We don't need to change any of these parameters for our example. So here we go. Now the inverse STFT outputs a wave. These are mono samples, and they are of data type float 16s. I'm going to convert them to float 32s just because that's what TF, that IO.write file works with. Yeah, I need a Lambda Layer for that. And I'm going to cast M to TF.float32. Sweet. So great. So the output is these float32 values. It looks good. Let's instantiate a model out of it. Equals where the input is the synth input and the output is the synth output. Let's give it a name and let's print it out. Great. So it takes the 8-dimensional input, then creates a spectrographic image of it, then lambda, and then it outputs a one-channel spectrogram because it's complex numbers. Does the STFT. The reason why this is none is because it's always going to be slightly different lengths. It's never like the exact same length, so don't worry about it. Cool. So now we're ready to generate samples. If you recall, the input to our synth, right, is going to be a one-dimensional array of like 8 values. Right? And these are going to be positive or negative. We don't fully know how far and wide they go, but I found that you can try different values here. You're going to get a different set of sounds. You know, some of them, you know, I'll set like the standard deviation to be like 50 or something like that and get like super varied numbers. So these things can go pretty high. They can go up to like, you know, 40, you know, and then this one will be like -10 and, you know, etc. So what I'm doing in this line here, I'm going to make a normally distributed random sample of 25 values of 8 dimensions each with a mean of 0 and a standard deviation of 2. And if we print those, this is what we get. So just imagine if you had a user interface for this, these would be your knobs or your sliders. Sweet. So let's now that we have like a bunch of random vectors, let's predict them. Let's just run our synth and see what it comes up with. Okay, seems to have worked. And now I'm gonna run this this is going to go for every output here, which is going to be 25, right? Because whenever you run a TensorFlow model or a Keras model, the output is an array of results. So this is an array of waves. If you'd like to see it, I'll just print it here. These are just samples. So we have our waves. We're going to go from, for every single wave there, we're going to, oh, this is superfluous here. We're going to encode wave into a wave file and save it. It's going to be saved right here. Wow, that was fast. It takes a second, and you will see all of the files in here. See if it. Here we go. All right, so let's listen to them, see what happens. I don't know if you're able to hear the sounds that I'm making, but I hope that you have some sounds in your notebook as well. If you want, you can always download these waves and import them into your DAW or something like that, play around with them. Awesome, glad. So you can imagine, like, every single sample that I used in this data set was strictly a synth sample, you know, a stab or a pad or something like that. But like, you could do it with like drum sounds if you wanted, right? You can make like a data set that is only drum sounds, and this thing will approximate some kind of drum sound, you know. Cool. So yeah, let's just try one. I'm gonna. If I rerun, I'm gonna delete this output here, and if I rerun this, then it'll give me another random set of vectors, and then we can generate another set of sounds until you can do this until you find the sounds that you actually want to keep. So let's tweak this a little bit. Let's see what happens if like I make this -1, I don't know, when keep this standard deviation of 2. Let's see what happens. Do that. Let me delete this in here. So I already ran that, rerun this, and then rerun this. All right, let's see what we got here now. Huh. These have like a little bit of faster decay. It's kind of a little tube sound, you know. Dies a little bit faster. Oh, that's cool too. So because you have a sound like this, right? It has like a very like a high attack value, and something like this, it has a low attack value. I can tell that if I was able to take the vector that represents this sound and the vector that represents this sound, right, and interpolate between them, I could basically sculpt that sound, you know. I can tell already that the model has been able to learn how to do like some sort of, envelope filtering. I like this one. It's got like a weird metallic sound. So I'm going to download that one. And I'm going to load it into I'm just going to load it here and see what it's like. If you're able to hear that. So yeah, that's pretty fun. Let's see what else we have. Was completely flipped. Well, there it is. All right. So it looks like. Dun, 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 dun. So there it is. You know, I mean, you can. I'd recommend you export this notebook because it has your models in there. But real quick, I'm gonna go over how to just use the ones that I already coded up in my repo. If you want to do this at home and you don't want to spend like 2 hours typing this up. There is, yes. So when you train this at home and you run, you should run TensorBoard, because if you use the Spectrogram Callback that I'm including here, this is going to let you compare in real time the inputs to the outputs, right? These are the reconstructions, and see how they do over time. You know, you're gonna be able to see like how close they get, how much they deviate. You're gonna be able to go to the audio tab and you can be like, listen to the input, you know, and then and listen to the output and compare them over time and see how they change. They're not going to be so great. I'm just going to tell you that. It's not going to be like, some of them are going to sound nothing like the original, and that's super frustrating. The way to fix that, it would be to make a more complex model. You're going to need more than 16 filters. You're going to need like, 128 filters, 256. I would try maybe doubling some of these convolutional layers just to learn like more deep features. Yeah, in an ideal world, they would sound exactly the same. But given that they don't, I'm kind of happy where it's going, you know? I can probably run it again and do like another 50 epochs, probably be a little bit better. You can also change like the mean and standard deviation here, see like, explore a little bit more, see what else you can get. I'm gonna do one more cell here. There's a function that I wrote called getModels that gives you the STFT, the encoder, and the decoder, and the autoencoder. And here you can just say like what kind of latent dimension you want it to be, the sampling rate, the duration, and these other parameters. And everything that we did in this exercise, it's already been done in this function, and it's outputted here. So if you don't want to deal, you can always just use this. Let's see what else we got. It's only one. I must have changed this. Sorry, guys. It's like this. Just the autoencoder is, you get this model, and now you can just compile it. You know, put your optimizer there. You can fit it. You know, the autoencoder has models in it. And you can see, they're already done. Another useful function you'll find is get the synth model. So like you input the decoder. So you would go like this. And then you call get synth model. And now this synth can predict your, you know, so you can imagine like if you were able to make an interface for this is how you would do it, you know. If you go into the GitHub repo, there's a script called train. You can run that if you want to train this. You will need to set the directory of the sample where you have your sample data set. You can download mine or you can use yours, whichever you would like. Then there's also a script in the GitHub repo called synth. There's this script in the GitHub repo called synth, and you can run this and it'll generate 25 random files for you using the model that's been pre-trained. This is in the GitHub repo, so if you clone the repo, it'll come with this. Or if you want to make your own, just run this train script and you should be good. If you want to learn more, like if you want to learn about Kapre, this is a great open source project. There's a lot of cool layers because you can do really interesting things with this, right? Like the way that we did it isn't the only way to do this. You could like transform these spectrograms into like something like, you know, MFCCs or something like that, or like a chromogram or something, see if that makes a difference or difference in the sounds that it makes. So Kapre is a recommend you read this paper, and this paper, autoencoding neural networks as musical audio synthesizers, was like the inspiration behind this. We did things a little bit differently, but nonetheless, there's like good information here. Simon says, have you tried playing around with encoding individual frames? Maybe it's never small enough. Yeah, totally. Yeah, so this is what I wanted to try next, is basically have like a single cycle of a wave rather than like taking a full-on sample that's like a whole second. I want to take just one cycle of like a sine wave and one cycle of a square wave, etc., and train it on just those so that it learns the features of that, and then just repeat it so that I can make waveforms of arbitrary length. And that would definitely be completely suitable for real time, you know. So that could be cool. Put it like in a Raspberry Pi and like make a cool synth out of it. All right, so if you are there any does anyone have any questions or like other comments? You're welcome. It's been fun, guys. Oh yeah. Yeah, and these waveforms are like super gnarly too. That's what I like about them. Like they're really dirty. Yeah. Cool. Well, I'm glad you all enjoyed it. If you want to chat, feel free to email me, or nice way to reach me is just tweet at me or send me a message on Instagram. I know that the my website has a contact form, but it's actually broken right now, and I've been too lazy to fix it. So like, just tweet at me sometime or whatever, and if you want to chat about stuff like this, or if you've made like cool music with any of these things, I would love to see it. Maybe I'm gonna in the next maybe month or two, I'm gonna try to make like an interface for this in Max. So. Oh yeah, just hit me up on Discord. Um, um, Anything we need to get to run the repo code. You should install Python 3, 3.7 if you can. And let me show you something quickly. This comes with a file called requirements. And these are the libraries that should be installed when you if you want to run this project. So like you can download the repo and run pip install -r requirements.txt, and this will install the dependencies. And then you should be good to go. If you don't have a GPU, this is going to take a long time. It'll take like maybe 2 minutes per epoch, which is not great. If you have a GPU for like gaming or whatever, it'll be a breeze. So great. So it's been fun. I hope I get to see you all again, and we can do some more hacking. And thank you all for coming today. See ya.